Hi folks, we're going to take a look at page 554, number 14. So here they gave us the equation of two lines, and in part A they want us to find the point of intersection, and then in part B they're looking for the equation of another line, so we'll take a look at that later on. So let's start with part A, the point of intersection. Alright, so in order to solve that, the first thing I would suggest doing is putting these equations in parametric form. Okay, so we take a look at the first line. We've got x is equal to 1 plus 3t. Okay, y is equal to -1 plus 2t, and then z is equal to 1 plus t. All right, so I'll call this x1, y1, z1. All right, and let's do the same thing now for the second line. So here we have -2 plus s. Okay, for y, -3 plus 2s. And then for z, we've got 0 plus 3s. All right, and so what we want to do is find the point of intersection. In other words, we need this x1, y1, z1 to be the same as the x2, y2, z2. Okay, so what that allows us to do is to equate the two x values, the two y values, the two z values. But since I've only got two unknowns with three equations, I can only work with one at a time. With two at a time. All right, so I'm going to take a look, and I'm going to see, I guess these two look a little easier. I can get rid of the t's. Either way, should be fairly easy to solve. So I'm going to let equation 1 here be the equivalence between the two y values. So -1 plus 2t is equal to -3 plus 2s. And then equation 2 here will be 1 plus t equals 3s. All right, so here I'm going to multiply equation 2 times 2 in order to eliminate the t's. So 2 times equation 2. So what do we have? We have 2 plus 2t equals 6s. And now I'm going to subtract 1 and 2. So here I'm going to do 1 minus 2 times equation 2. All right, so here we have -1 minus 2 is -3. 2t minus 2t is 0. And then here we have -3 minus nothing, so -3. And then 2s minus 6s is -4s. All right, and here I end up with -4s equals, well, -3 minus -3, plus 3, when I bring that to the other side, is just going to be 0. So that means s is equal to 0. So that's nice and easy. And then I'll take equation 2 and I'll solve for t. So if I take equation 2 here, I have 1 plus t is equal to 3 times s, which is 0. So t is just equal to -1. All right, so this is where we have to be careful, because this is the s and t values that make the y's and z's equal. I need to make sure that these same s and t values make the x values the same. So this, I'm going to do my little check here. All right, so if I take x1, I have 1 plus 3t, okay, which is -1. So 1 minus 3 is -2. And then x2 is -2 plus s, -2 plus s, which we found to be 0. And again, we have -2. So it means that these are indeed intersecting lines. By the way, quick look to see that they're clearly not parallel. All right, so now I found the x value. So to find the point of intersection, all right, I already found the x value. Now for the y and z value, doesn't matter which equation I use, but since s is equal to 0 here, I think it makes more sense to use these equations. So -2 plus 0, we already have that. -3 plus 2 times 0 is just 0, so -3. And then here, 3 times 0 is just 0. So there's my point of intersection, and that's part A. All right, so let's look at part B here. So now let's read a little more carefully. So we're looking for the vector equation of a line. So we're looking for a line that's perpendicular to both of these lines and passes through the point of intersection. So to find the equation of a line, I need a point. So I have my point. It's -2, -3, 0. What I need now is a direction vector. All right. Let's see what we have here. If I've got two lines that intersect at a point, all right, I need, let's see if I can find something a little smaller. Okay, I need to find the line that's perpendicular to this here. So in other words, the direction vector that I'm looking for needs to be perpendicular to both of those lines. Well, what's going to be perpendicular to both of those lines? Well, the cross product of their direction vectors is going to be a vector perpendicular to both. Okay, so to find this direction vector, I'm actually just going to take the cross product of my original two direction vectors from two equations here. So let's do that on the side. So I've got 3, 2, 1. And then here I've got 1, 2, 3, 3 and 1. So let's calculate the cross product. So what do we have? We have 6 minus 2 is 4. Here we've got 1 minus 9 is negative 8. And here I have 6 minus 2 is 4. So what I'm going to use here is my direction vector. I might as well simplify it since I can use any direction vectors. I'll divide this by 4. So I have 1, negative 2, and 1. And now that I have the point on this line, which was the point of intersection of those two, I have a direction vector for this line I'm looking for, which is perpendicular to the direction vectors of both of those two lines. I can now write out my answer. So R here is going to be equal to negative 2, negative 3, 0, plus, now since we've used S and T already, I'll use something else. I'll say P times my direction vector 1, negative 2, 1, where P can be any real number. Okay, and let's just take a look. I was looking for the vector equation, so I don't have to write out one of the other two. So just to recap here, step number 1, when you find the point of intersection between two lines, you work with the parametric equations with different variables in each, but I can only work with 2 at a time. Here I chose to work with y and z. Once I solve for my unknowns s and t, I always have to check to make sure that the x components are indeed the same. Okay, and if they are, I can go ahead and find my point of intersection. Here, because I was looking for a new line that was perpendicular to the two original ones, I could just find the direction vector of the line I'm looking for by taking the cross product of the original direction vectors. Okay, that's it for this one.